On a Monday night, the sky above Buenos Aires was transformed by an otherworldly green glow. A brilliant, violent fireball tore through the atmosphere at 40,000 kilometers per hour, a silent electric streak across one of the most populous urban centers in the Western Hemisphere. It was an event captured from countless angles by security cameras across the city. The speed was logged by AccuWeather, and then, before the questions could even fully form, it happened again. Within 48 hours, the skies over British Columbia put on a similar display, with over 100 reports filed before many had even started their day. And then came a third green light, this time above Hawaii. The same narrow time frame, the same haunting color, and the same perplexing silence from the official databases designed to track these exact phenomena. We are witnessing events across 3 continents in just 72 hours, all occurring within a window that, according to the only existing peer-reviewed science on the matter, should have closed on April 7th. We are now 20 days past that deadline. The model predicted an end, but the solar system seems to have had other plans. As this was all unfolding, a 5-meter asteroid slipped quietly past Earth, moving inside our own satellite ring without a single public warning. This is far more than a story about fireballs. The science suggests this surge should be over, which raises a profound question. What is our planet still flying through? If this mystery has already captured your attention, we invite you to join us here on Calm Space, because this story is only just beginning. The model may have ended on April 7th, but the fireballs did not. New events are still being reported, and the data is undergoing analysis. The deeper we look into this emerging pattern, the more critical it becomes to have someone connecting the pieces. Something truly extraordinary lit up the night over Buenos Aires on the 27th of April, 2026. For a few stunning seconds, a single thought likely crossed the minds of 13 million people. What was that? There had been no warning, no official announcement, no countdown to a celestial event. There was only the darkness, and then a sudden, overwhelming light. It was a violent electric green that momentarily turned the night sky into a strange, disorienting daylight. Just as quickly as it appeared, it vanished, leaving a vast city staring upward, with a shared, unanswered question hanging in the air. To grasp the significance of this moment, let's begin with the raw facts, as they alone are enough to command our attention. The event took place at approximately 10:51 p.m. local time on April 27th. The object was officially classified as a green bolide, a specific type of meteoroid that, upon entering the atmosphere, burns with a distinctive, almost emerald luminescence due to its composition and extreme speed. AccuWeather recorded its entry velocity at more than 40,000 kilometers per hour, which translates to roughly 11 kilometers for every second it traveled. To put that into perspective, in the time it takes you to simply blink, that object had already covered a distance greater than the length of most major airport runways. It didn't just drift across the sky. It punched its way through the atmosphere as if it had a destination and no patience for the journey. This was not a fleeting glimpse witnessed by only a few. A vast network of security cameras all across the sprawling city captured the event from multiple perspectives. Independent footage from dashboard cameras, home surveillance systems, and public street monitors all corroborated what hundreds of eyewitnesses on the ground were already reporting. They described a brilliant, fast-moving light that left behind a persistent vapor trail. Some observers even noted what they called a plasma cap preceding the object, a feature that speaks directly to its nature. A plasma cap is a telltale sign of an object that is neither small nor slow, suggesting significant mass and incredible velocity. And it is here that the story takes its first, truly puzzling turn. As of this report, the American Meteor Society, which serves as the primary English language database for fireball events in the Western Hemisphere, contained 0 entries for this incident. Absolutely none. An object that blazed across the sky of one of the most densely populated urban areas on the continent, seen by potentially millions of people and recorded by dozens of independent cameras, simply did not exist in the official records. We will return to this point, because it is more than just an administrative gap. It suggests an uncomfortable discrepancy between what we believe we know and what our systems are actually measuring. Now, hold that thought, because within 48 hours, the sky performed this feat again. This time, the stage was British Columbia, Canada. On April 29th, a second fireball appeared. It was on a different continent, moving in a different direction, and seen by a different population, but it displayed a similar brightness, exhibited similar behavior, and glowed with that same characteristic green signature. On this occasion, however, the American Meteor Society did log the event. More than 100 reports flooded the system in less than a day. Witnesses all across the Canadian province described the same kind of rapid, intensely bright, greenish streak that Buenos Aires had seen just 2 days prior. By the AMS's own standards, over 100 reports in under 24 hours constitutes a significant event, one that was properly recorded and counted. Then, overlapping with both of these occurrences, within that same narrow 8 to 7 2-hour window, a third signal emerged. This one came from the skies above Hawaii, specifically over the Kona area. A green light was filmed crossing the sky, with the footage circulating on social media and generating the kind of confused attention that such unusual aerial phenomena often do. Was it another meteoroid from the same stream? Was it a piece of re-entering satellite debris? Or could it have been something else entirely? While its classification remains uncertain, its timing is what makes it so difficult to dismiss as mere coincidence. We have 3 unusual celestial events over South America, the Pacific Northwest, and the Central Pacific, all clustered within a 3-day period. When you begin to map the geographic spread of these incidents, the sheer scale of the pattern becomes clear. Buenos Aires is situated at roughly 60 degrees west longitude. British Columbia is located around 125 degrees west, and Hawaii is near 155 degrees west. Spreading these points out on a globe reveals events distributed across nearly 200 degrees of longitude in less than 3 days. That represents a journey more than halfway around the Earth's circumference. These were not localized phenomena, confined to one part of the sky or one corner of the planet. They arrived from different directions, on different trajectories, and were seen by different populations. Yet they all happened in the same brief slice of time. That pattern is undeniably important. And it becomes even more significant when you add the next layer of context. Here is the piece of the puzzle that almost no one is connecting right now, and it is the very reason for this report. There is exactly one peer-reviewed scientific paper that has attempted to explain the dramatic surge in fireball activity that began in March of 2026. Just one. It was authored by a researcher named Patrick M. A scientific paper published in October presented a compelling new model. It detailed a newly identified debris stream, which was given the designation M2026A1. The model traced its origin to what it termed a rock comet, an asteroid that begins to act like a comet as it is heated by the sun, shedding fragments that spread out along its orbital path. The research, which was based on 282 meteor detections from coordinated global networks, underwent a rigorous peer review process. It offered a very specific window of activity, a period when Earth was predicted to pass through this stream of debris, from March 16th to the 7th of April, 2026. Yet, this is where the story takes an unexpected turn. The fireball over Buenos Aires occurred on April 27th. The one over British Columbia followed on April 29th, with the event in Hawaii overlapping them. These fireballs appeared 20 to 22 days after the model predicted the stream's activity would end. This wasn't a minor discrepancy of a day or two, it was a gap of more than 3 weeks. This timing conflict presents a profound puzzle. If the debris stream's window was indeed closed, then what is Earth continuing to fly through? This is not a rhetorical device or an opener designed for alarm, but a genuine, unanswered scientific question that our current data cannot fully resolve. We are left with a precise model and a specific time frame, yet we are also faced with real-world events that fall well outside that window. The frequency and timing of these events suggest they are more than just coincidence, background noise, or the natural tapering of a meteor shower. The data and the model seem to be telling two different stories, and the discrepancy between them is the central mystery we must now explore. Throughout this journey on Calm Space, we will carefully examine what the data truly reveals and what the model actually forecast. We will investigate the gap that exists between these two perspectives and consider what it could signify, not only for the events of this past April, but for our wider understanding of the cosmic environment Earth is currently navigating. Along the way, we will encounter some genuinely concerning realities about our planetary awareness. We will touch on how we detect fireballs, and perhaps more importantly, what we miss. This includes a recent incident where a 5-meter asteroid passed Earth inside the orbit of our geostationary satellites, without a single public warning being issued. We will also look at the data systems that carry immense scientific importance, yet cover less than 1/3 of our planet's surface. We know that something unusual is taking place. The data we have confirms it. We have a model that provides a partial explanation, but then it falls short. And we have a planet equipped with detection systems that were not built for the kind of activity we now appear to be witnessing. The window of activity was supposed to have closed. It did not. And that simple fact means we must begin to ask different and more urgent questions. Let us return to the event over Buenos Aires, because it is essential to reframe what happened there. Instead of seeing it as just a spectacular light show, we should view it as a critical failure in measurement. When a brilliant fireball streaks across the sky above a major city, the scientific community typically learns of it through a collection of reports. These are witness accounts submitted to databases like the American Meteor Society, footage from security cameras that gets uploaded and shared, and news articles that provide specific times and locations. This raw data is what scientists depend on to reconstruct a fireball's trajectory, estimate its mass, and classify the event. From the perspective of the official scientific record, if an event goes unreported, it might as well have never happened. The volume of reports an event generates is not a random variable. It is generally proportional to several key factors: the number of people who witnessed it, the technological and cultural infrastructure available for reporting it, and the existing awareness within that population about what to do when they observe something unusual in the sky. The metropolitan area of Buenos Aires is home to somewhere between 13 and 15 million people, making it one of the most populous urban centers in the Western Hemisphere. Its greater metropolitan region is densely developed, widely monitored by security cameras, and interconnected by modern communications. When a brilliant object illuminates the sky over Buenos Aires at 11 p.m. on a clear night, the potential for millions of people to see it is very real. Based on events of similar brightness over comparably populated areas in North America and Europe, the statistical expectation would be for the American Meteor Society to receive somewhere between 50 and 150 reports. This, it should be noted, is a conservative estimate. The actual number of AMS reports filed for the Buenos Aires event at the time of this recording was 0. Not a small number, not a handful. 0. Now, before concluding that something nefarious is at play, let's consider the entirely mundane explanation. In many ways, the reality is more disturbing than any cover-up. The American Meteor Society is an English-language platform. Its primary user base is concentrated in North America and, to a lesser degree, Western Europe. The reporting interface, the public outreach, and the cultural presence of the AMS are all optimized for a specific geographic and linguistic segment of the global population. As a result, South America, as a whole, is dramatically underrepresented in AMS data relative to its population and skywatching activity. An event over Buenos Aires that generates extensive local coverage in Spanish-language media does not automatically translate into entries in the AMS database, simply because the pipeline between the witness and the database was never designed with that witness in mind. This phenomenon is what scientists sometimes refer to as dark data. This is not data that has been actively suppressed, but rather data that was generated, observed, and even recorded, but never found its way into the systems we rely upon for our understanding of near-Earth space. The Buenos Aires fireball is a perfect illustration of this concept. The event was confirmed by multiple independent video recordings. AccuWeather tracked it. Local social media platforms were filled with witness accounts. Every component of a well-documented fireball event was present. And yet, from the viewpoint of the world's most widely cited fireball database, the event simply does not exist. Here is why this is so critical to the central question we are pursuing. We are already examining April 2026 as a month, with major fireball events running at 2.5 times the historical baseline. That startling figure is derived from AMS data. It only counts events that generated a significant number of reports within that specific database. It does not include events that were seen and logged locally in countries with lower database engagement. It does not count events over the ocean, which covers 71% of our planet's surface. And, crucially, it does not count the Buenos Aires bolide. The data we have is concerning, but the data we are missing suggests the reality may be even more profound. When we hear that April's activity is tracking at 2.5 times the baseline, it's crucial to see that figure as a starting point, not a final tally. This number represents a flaw, suggesting the true rate of significant fireball events during April 2026 was, at a minimum, 250% of the historical average, and very likely much higher. It raises a critical question about the data we might be missing. Let's look at what the physical characteristics of the Buenos Aires event actually tell us. A key feature was its persistent vapor trail, the glowing channel of ionized gas left in a meteoroid's wake. The duration of this trail, which can last from seconds to minutes, often corresponds to an object's size, speed, and angle of entry. A long-lasting trail, like the one witnessed, points to an object of considerable substance, one that held together as it journeyed through the upper atmosphere instead of breaking apart upon impact. Furthermore, witnesses reported a plasma cap, a luminous shroud at the object's leading edge. This phenomenon is consistent with a very fast-moving body generating a shock-heated bubble of gas as it compresses the increasingly dense air in its path. Also telling is what the footage does not show: any obvious signs of fragmentation. Many fireball events are characterized by the parent body shattering into multiple pieces, which then spread out and flare brightly. The footage from Buenos Aires, however, depicts a single, coherent object maintaining a steady trajectory. This suggests one of two possibilities. Either the meteoroid was exceptionally robust in its structure, or it was traveling so fast for its size that it was consumed primarily by ablation, the process of its surface layers burning away rather than by mechanical stress. In either case, the interpretation leads to the same conclusion. This was an object of significant size and density. Then there is the matter of its color. The distinct green hue observed during the event is a well-known spectral signature in fireballs, typically attributed to the presence of magnesium. Specifically, it corresponds to the emission lines of ionized magnesium at a wavelength of approximately 518 nanometers, placing it squarely in the green portion of the visible spectrum. While a magnesium-rich composition is not unusual for meteoroids and is quite common in stony objects, its appearance in this context becomes particularly intriguing. The context is what makes this detail so significant. Just 2 days later, the fireball over British Columbia was also described as having a green signature. The event over Hawaii shared this same characteristic. Here we have 3 separate events occurring within a 72-hour window and spanning nearly 200 degrees of longitude, all displaying the same spectral marker. Could this be a coincidence? It is certainly possible, as common compositions can appear in unrelated objects. But it also raises the compelling possibility of a shared origin, that these were fragments from a single parent body, or pieces of a larger debris field with a uniform mineralogy. And this possibility points directly back to the central mystery. If these events do indeed share a compositional origin linked to a specific debris field, the implications are profound. That field was predicted to have cleared Earth's orbit 20 days earlier. This discrepancy suggests that either the field is far larger than our models accounted for, or we are encountering multiple, uncharacterized debris fields. A third possibility is that our fundamental understanding of how these streams of material disperse through space is incomplete. Each of these scenarios challenges our current picture of the near-Earth environment. The absence of a coordinated trajectory analysis for the Buenos Aires event represents another critical gap in the data. With numerous independent video recordings from different vantage points across a major city, it is technically feasible to reconstruct the object's approximate path, its angle of entry, and even its pre-atmospheric orbit. This is precisely the method scientists have used to link other recent fireballs to specific debris streams. Yet, this reconstruction requires dedicated effort. It requires the event to be recognized as scientifically important, and for the footage to be collected, calibrated, and analyzed. For the Buenos Aires fireball, that work had not been done, leaving a crucial data point existing only in theory, not in practice. This absence of data is not a neutral silence. It is a form of distortion. It creates a warped perception of near-Earth space, one that is systematically skewed toward the regions where we have built our instruments and designed our reporting systems. It's a view that overrepresents some parts of the world while leaving others in shadow. When we are trying to determine if a surge in debris has truly ended or if it is continuing at an intensity that defies our predictions, this distortion is more than a minor inconvenience. It represents the difference between believing we understand the situation and actually understanding it. Herein lies the unsettling implication at the heart of this issue. If the brilliant Buenos Aires fireball is effectively dark data, real, confirmed, but uncounted in official logs, then it forces us to ask, how many other events have gone unrecorded? How many powerful bolides have streaked across the skies of southern Africa, Central Asia, the Amazon basin, or the vast South Pacific, unseen by our formal networks? We are attempting to track an anomaly with instruments that provide effective coverage for perhaps only 30 to 40% of the planet's sky. And even with this partial, fragmented view, the anomaly is already outpacing our best models. This was the picture from South America. Now, let's cross to Canada, where the same week looks completely different. Not because the sky behaved differently, but because the infrastructure did. The fireball over British Columbia, for instance, entered the American Meteor Society database with remarkable speed. Over 100 reports were filed in less than 24 hours. By the time news of the event was spreading on social media, the data was already being formally processed. This efficiency is no accident. It is the result of years of dedicated public outreach. Sky watchers in North America are culturally conditioned to report these phenomena. A network of apps, websites, social media groups, and astronomy clubs all feed into a data pipeline designed specifically to capture this kind of information. When a bright light crosses the sky over Vancouver Island, thousands of people know exactly where to log their experience. The system works as intended. Now, place that response alongside the one for the Buenos Aires event. The difference was not that the Argentinian fireball was less real, less bright, or less significant. By all available evidence, it was at least comparable in magnitude, and perhaps even more dramatic. The disparity was not in the sky, it was on the ground. It lay in the reporting culture, the language of the reporting platforms, the geographic scope of the outreach networks, and the simple historical fact that the American Meteor Society was established by and for a primarily North American, English-speaking community. This fundamental asymmetry in our global observation network has profound consequences. It directly affects how we perceive and understand the current surge, creating a picture that may be dangerously incomplete. Any statistical model, including those used to analyze the current fireball anomaly, is fundamentally shaped by the data it is fed. In this case, our primary databases are heavily weighted toward observations from North America and Western Europe. This geographic skew introduces a critical uncertainty. When scientists describe the events of March 2026 as a 4.12 sigma anomaly, they are comparing recent activity to a historical baseline that is itself a product of this same regional bias. We are essentially measuring a new number against an old one, both drawn from an incomplete global sample. The practical implication is profound. The true scale of the current surge in fireball events is almost certainly greater than what our official records indicate. The figure of 2.5 times the baseline for April is derived from a dataset that overlooks 71% of the Earth's surface and substantially undercounts events over vast, inhabited areas. If we had the means to detect every major fireball with equal efficiency across the globe, irrespective of geography, language, or infrastructure, that number might be 3 or even 4 times the baseline. The truth is, we simply do not know, and this uncertainty dramatically complicates our efforts to determine if this phenomenon is waning or persisting. This data deficiency directly impacts our understanding of the M2026 A1 event window. The prevailing model had predicted that the heightened activity would conclude by April 7th, yet the database clearly shows it continuing long after that date. The problem, however, may be even more significant than it appears. The database is known to underreport activity in the Southern Hemisphere and other regions where reporting systems are less developed. If the post-window events are occurring disproportionately in these undercounted areas, a possibility hinted at by the geographic distribution of events in April, then the model's predictions are not just slightly off, but profoundly incorrect. The disparity between the fireball recorded over British Columbia and the one missed over Argentina is more than a simple quirk of record keeping. It is a clear window into the structural limitations of our entire global monitoring system. We possess highly effective detection networks in some places and virtually none in others, yet we use data from the well-monitored zones to make pronouncements about the entire planet. The sky treated both events equally, but our systems did not. This fundamental asymmetry helps explain why we continue to be surprised. Not necessarily because the events themselves are without precedent, but because our tools were not built to measure a phenomenon of this scale. The conclusion is as unavoidable as it is unsettling. The anomaly is almost certainly larger than reported, and the window of activity that was meant to have closed weeks ago may, in fact, remain wide open. we are left peering at a phenomenon that we can only partially see. This brings us to a third, more elusive signal that emerged from Hawaii, a quieter, less certain observation that nevertheless falls within that same impossible timeframe. Part 4. The quiet third signal. Of the three events in this compelling cluster, the observation from Hawaii is the most ambiguous. It is vital to be precise about this uncertainty, because here, careful distinctions are more valuable than a tidy narrative. Within the same 48 to 7 2-hour period as the incidents in Buenos Aires and British Columbia, a green light was filmed traversing the night sky above the Kona district of Hawaii's Big Island. As is common in the digital age, fragments of footage and conflicting descriptions quickly spread across social media, sparking debates about whether it was a meteor, a satellite, or something else entirely. While multiple witnesses in the area reported seeing an unusual object, providing accounts consistent enough to be taken seriously, the event has yet to receive a confirmed classification in any major database as of this recording. It has not been formally identified as a meteoroid, nor has it been definitively ruled out as a piece of re-entering satellite debris or a spent rocket stage in its final, uncontrolled descent. No official monitoring network has assigned it a trajectory. For now, it occupies an uncomfortable scientific middle ground. Something clearly happened, but no one has officially determined what it was. It is worth pausing in this moment of ambiguity, for it is often more scientifically instructive than a clean and immediate classification. A fact that is not discussed often enough in public-facing coverage of fireballs is that not everything entering our atmosphere from space is a natural meteoroid. This distinction may seem elementary, but its consequences are profound when trying to interpret an event. Our planet is currently encircled by thousands of artificial objects. These include defunct satellites that have exhausted their fuel and are slowly spiraling downward, spent rocket bodies from launches dating back to the 1960s, and clouds of smaller fragments created by on-orbit collisions. These objects are constantly re-entering the atmosphere. While most are small enough to burn up completely unnoticed, a larger piece will occasionally make the descent. When this happens, it can create a visual spectacle that is, at first glance, very difficult to distinguish from a natural meteor. To an observer on the ground, the sight is often the same, a brilliant streak of light moving swiftly across the sky. They report what they see, and it is then up to the scientific databases to decipher the object's true nature. A witness sees a glowing trail, sometimes tinged with green or blue hues, as various metallic components vaporize in the intense heat of re-entry. The initial report is simply of a fast-moving light, but what was that light? This is the central question that analysts must answer. The distinguishing characteristics between a natural meteoroid and an artificial re-entry event are real and measurable, but applying them requires high-quality data. Velocity stands as the most reliable discriminator. Natural meteoroids slice into the atmosphere at immense speeds, ranging from a low of approximately 11 kilometers per second to a high of 72 kilometers per second, depending on their trajectory relative to Earth's own motion. In stark contrast, artificial debris re-enters at a much more leisurely pace, typically between 7 and 8 kilometers per second, the orbital velocity required to stay aloft in the first place. This dramatic difference in speed results in visibly different behaviors. A fast-moving natural meteoroid burns intensely and rapidly, often fragmenting violently as it succumbs to aerodynamic stress. A slower artificial re-entry, however, tends to produce a longer, more graceful arc and frequently breaks apart more cleanly, with multiple pieces drifting away as their different materials burn at different rates. The angle of the trajectory also provides crucial clues, helping scientists piece together the object's origin story. Natural meteoroids, arriving from the depths of interplanetary space, tend to strike our atmosphere at very steep angles. In contrast, artificial objects like defunct satellites or rocket stages fall out of decaying orbits, often creating much longer, more horizontal trails as they re-enter at shallower angles. But perhaps the most telling difference lies in how they come apart. An artificial re-entry is often characterized by the clean separation of large, recognizable components, a pattern quite distinct from the explosive disintegration of a rocky meteoroid under immense aerodynamic pressure. The footage from Hawaii, however, is consistent with either scenario, and that is the most honest assessment we can offer. The velocity of the object is genuinely difficult to measure from the video, as there are no calibration references in the frame. The trajectory angle is likewise ambiguous from the single perspective that was captured. The object's green glow, a feature we have previously discussed as a spectral signature of burning magnesium in natural meteors, is not a reliable guide here. This is because spacecraft and rocket bodies frequently use magnesium alloys in their construction, which produce the very same green luminescence upon burning. One simply cannot determine whether a green fireball is natural or artificial based on its color alone. The green hue confirms the presence of burning magnesium, but it reveals nothing about where that magnesium originated. Now, it is important to be direct about the role of this event in our story. We will not overstate its significance, nor will we use its ambiguity to build a narrative that goes beyond what the evidence can support. The Hawaii observation is presented here as a contextual detail, not as a primary piece of evidence. The core of our argument is built on much firmer ground, beginning with the event over Buenos Aires. This was a real phenomenon, confirmed by multiple independent video systems, logged by AQ weather monitoring, and witnessed by a vast urban population. It was characterized well enough to describe its persistent vapor trail and plasma cap. The event over British Columbia is equally real, substantiated by over 100 reports filed with the American Meteor Society and independently corroborated. These two occurrences are the foundation of the post-window argument. Even if we were to remove the Hawaii sighting from this account entirely, the central question would remain just as sharp and just as unanswered. So what then? Does the Hawaii observation contribute? It offers something more subtle, adding texture and density to this remarkable window of time. Within a 72-hour period, 3 highly unusual events were reported in the sky over 3 distinct geographical regions. The simple fact of this temporal clustering is itself a data point. It suggests something about the sheer intensity of that period, and it represents the kind of focused attention that strange atmospheric phenomena can generate when they happen in close succession. That attention, in turn, is part of how the scientific record itself is constructed. More importantly, the uncertainty surrounding the Hawaii event illustrates a challenge that compounds every other problem we have been discussing. Our difficulties in understanding the current surge are not just about gaps in reporting or geographical blind spots. We also face a profound classification uncertainty situations where an object enters the atmosphere, is filmed by real people in real places, and circulates through official reporting channels, yet still cannot be definitively categorized. This identification problem sits atop the detection problem, which rests on the reporting problem, which is itself influenced by the modeling problem. These are not separate issues. They are interconnected layers of the same structural limitation, and each layer makes the one beneath it harder to resolve. We are not always certain about what we are seeing, even when we can see it. That is a statement worth pausing to consider. In the case of Hawaii, we possess the footage, the witness accounts, the timestamp, and the location. And yet, we still cannot say with confidence whether the object that crossed the sky over Kona was a rock from space or a piece of human-built hardware on its final descent. This uncertainty is not a failure of any single scientist or monitoring network. It is a direct consequence of building our observational infrastructure for an expected set of phenomena, only to encounter conditions that stress the very boundaries of what that system was designed to handle. The Hawaii event adds one more layer of complexity to a picture that is already far too intricate for any single model to describe. It is a reminder that the question of what we are flying through is not just about the rocks themselves. It is about our capacity to see, identify, count, and ultimately understand them. And right now, that capacity is being pushed to its limits. This brings us to the model itself, the precise, peer-reviewed, and scientifically rigorous framework that provided a specific end date, a radiant cluster, and a physical mechanism for the event. This is the same model that then watched as 20 days of post-window events accumulated without offering any explanation for their existence. This is where the story becomes genuinely uncomfortable, and it is exactly where we are headed next. Part 5. March was not noise. Before we can fully grasp why the persistence of events into April is so significant, we must first understand what March truly was. It was more than just a string of viral fireball videos, social media clips of green streaks over cities, or the occasional news segment about a loud boom. We need to look at what March was statistically, when one sits down with the data and performs the math with care and honesty. The results are genuinely startling. Let us begin with the baseline. The American Meteor Society logs major fireball events, defined as those significant enough to generate over 100 witness reports. Historically, the average for such events is roughly 2 per month. This number, 2, is not a simple guess. It accounts for the natural variation in the meteor environment, the seasonal rhythms of Earth's orbit, and the predictable annual showers that cause activity to spike in certain months. The Perseids in August, the Leonids in November, and the Geminids in December are all well known and expected. Researchers who work with this data model these spikes and remove them from the baseline to arrive at that 2 per month figure, which represents the genuine background rate for major atmospheric entries not associated with known annual streams. In March of 2026, there were 12 such events. 12 major fireballs in a single month, against a baseline of 2. This was not a mild elevation, or a month where one could simply say conditions were slightly unusual. It was a profound deviation from the norm. The actual rate of these events was 6 times higher than what was anticipated. A researcher named Mike Hankey, who is known for conducting some of the most meticulous and careful public analyses of this phenomenon, formally calculated the statistical significance of this deviation. His findings placed it at approximately 4.5 sigma. For those who do not regularly work with standard deviations, it can be helpful to have a sense of scale. A 1 sigma event is a common fluctuation, essentially background noise. A 2 sigma event might briefly catch your eye. At 3 sigma, scientists begin to take serious notice and ask pointed questions. A 4 sigma result is rare enough to be considered strong preliminary evidence in most scientific fields that something truly unusual is happening. But a 4.5 sigma deviation is something else entirely. In a well-ordered scientific community, a number like that is a call to action. It prompts immediate investigations, discussions about emergency funding, and a serious re-evaluation of the fundamental models being used. This was not a statistical fluke or a minor seasonal variation. By any rational measure, it was an extreme outlier. Yet, it is crucial to understand that this headline figure, the 12 events versus the expected 2, the 4.5 sigma deviation, is actually the least remarkable part of what Hankey discovered. The complete story is far more disquieting. The data reveals that for the fireball events of March 2026, the rate of sonic booms reached an astonishing 79%. It is worth pausing to consider the implications of that number. Not every fireball is capable of producing a sonic boom. That phenomenon is reserved for objects that possess sufficient size and density, and that enter the atmosphere at an angle that allows them to penetrate deeply. Only then can the shock wave they generate travel all the way to the ground as audible sound. A small, fragile meteoroid, like the loosely bound collections of dust and ice that create most of the streaks in an annual meteor shower, will typically burn up high in the atmosphere, producing a beautiful flash of light, but no sound at ground level. The presence of a sonic boom, therefore, is the signature of a different class of object entirely. It signals something denser, heavier, and more structurally sound, the kind of body that does not simply disintegrate upon entry. Instead, it pushes deeper into the atmosphere, compressing the air before it so violently that a powerful pressure wave is sent rolling across the landscape below. A typical major fireball event generates a sonic boom far less frequently than 79% of the time. The fact that the march rate was so exceptionally high tells us something specific and vital about the physical nature of these objects. These were not ethereal particles or delicate aggregates of cometary dust. The evidence strongly suggests they were solid rocks, dense and mechanically robust enough to withstand the initial shock of atmospheric entry and penetrate far deeper before they finally broke apart or burned out. The size distribution for the March events was noticeably skewed toward the larger end of the spectrum for small celestial bodies. This characteristic, this tendency toward larger sizes, becomes enormously important when trying to determine the origin of the object population that Earth had encountered. Then we come to the duration data, a detail that perhaps best illustrates the true scope of what occurred in March, yet it is almost always omitted from popular discussions of the event. Before March 2026, the all-time record for long-duration fireball events recorded by the American Meteor Society in a single month was 651. These are defined as fireballs whose visible, luminous phase lasts for more than a second or two. This extended brightness implies an object that is either large enough or slow enough to sustain its ablation across a long atmospheric path, rather than just exploding in a brief, intense flash. That number, 651, represented the previous high water mark. It was the benchmark for an extraordinarily active month. In March 2026, the American Meteor Society logged 1,693 long-duration events. That figure, 1,693 against a previous record of 651, is not merely breaking a record. It is a complete obliteration of it. It represents a value more than 2.5 times the previous peak, in a category that specifically tracks the larger and more substantial objects. This occurred in the very same month that saw 12 major events against a baseline of 2, a 4.5 sigma deviation in frequency, and a 79% sonic boom rate, which confirmed these were heavy, ground-shaking rocks. When viewed together, these 3 data points cease to look like a statistical anomaly. Instead, they form a coherent physical signal, with each piece of evidence pointing in the same direction. In March of 2026, our planet moved through an elevated stream of objects that were larger than average, possessed greater structural integrity, and arrived in numbers so far beyond historical precedent that the word anomaly seems utterly inadequate. The radiant data adds yet another layer to this unfolding mystery. A fireball's radiant is the point in the sky from which its trajectory appears to originate. It acts as a celestial fingerprint, telling astronomers where an object came from. Objects belonging to the same debris stream will share a common radiant, appearing to arrive from the same patch of the sky along parallel paths, much like raindrops driven by a single wind. Conversely, objects from different sources will have different radiants. The analysis for March 2026 revealed a doubling in what are known as high declination events. These are fireballs arriving from regions of the sky that are relatively uncommon in the historical data directions that do not align with the well-documented annual meteor streams whose paths are already understood. This doubling of unusual arrival directions is significant in its own right. However, the most profound detail from the radiant data involves two specific events that stand apart from all the others. During that month, two separate fireballs were so substantial that they produced meteorite falls, meaning physical fragments survived the journey through the atmosphere and reached the ground. An event that yields a meteorite is already rare, requiring a precise combination of size, composition, and entry velocity to allow pieces to slow down and land intact rather than vaporizing. Having two such events in a single month is statistically notable. But the truly astonishing fact is that the radiance of these two meteorite-producing events were separated by approximately 98 degrees. To visualize this, imagine standing at the center of a vast clock face. If one object arrived from the direction of the number 10, the other arrived from the direction of the number 7. The angular separation in question is immense, approaching 100 degrees across the sky. This simple fact presents a profound geometric puzzle. Two distinct meteorite-producing events, occurring within the same calendar month but originating from such widely divergent points, cannot logically belong to a single, narrow debris stream. Basic orbital mechanics dictates that objects traveling together on the same track cannot arrive from directions so far apart. After a meticulous analysis, where he accounted for every conceivable observational bias from reporting improvements and population shifts to seasonal factors and instrument sensitivity, researcher Hankey arrived at a firm conclusion. The March anomaly was not an illusion. It was a genuine, robust, and multidimensional phenomenon, confirmed independently by four separate streams of data: event frequency, atmospheric duration, sonic boom rates, and radian distribution. When so many independent measurements all point to the same conclusion, scientists recognize it as a powerful and reliable result. This is precisely why the events of March are so critical to understanding the April story that followed. If March represented a genuine 4.5 sigma spike in activity, and the data strongly suggests it did, then April's failure to return to normal conditions is not a mere statistical footnote. It is the second chapter of a pattern, one that the M2026A1 model was only designed to describe the first chapter of. That model successfully captured the March event and set a clear boundary for its conclusion on April 7th, but reality simply kept going. March was not random noise. It was a signal so loud and unambiguous that to dismiss it would require deliberately ignoring multiple independent data streams. The central question, upon which this entire narrative hinges, is what to make of April. Was it merely an echo of the March signal fading into silence? A continuation of that same signal at a sustained intensity? Or was it something new entirely, driven by forces the original model never considered? As we are about to see, the evidence does not point towards silence. Part 6. April. The failure to return to baseline. Whenever an anomaly occurs in Earth's debris environment, there is an implicit understanding, a predictable rhythm to the encounter. An unusual event begins, activity spikes, and scientists work to identify its source. As Earth moves through the densest part of the material, the numbers reach a peak. Then, because our planet's motion is constant and orbital mechanics are relentlessly precise, the curve inevitably comes back down. The stream has a finite width, and as Earth crosses it at a known velocity, the anomaly resolves and the event is filed into the historical record. This is the established pattern for the Perseids each August and the Leonids every November. In fact, this is how virtually every documented debris stream interaction has worked throughout the history of meteor science. The spike is bounded, defined by a clear geometry with a beginning, a dense middle, and a tapering end that fades predictably back into the background. April of 2026, however, does not resemble a decaying spike. It shows no indication of being a thinning end or a return to the baseline. The longer the month progressed, the more apparent this deviation became. By the time of this recording, with several days still left in April, the American Meteor Society database had already logged 5 or more major fireball events for the month. These are incidents that cross the 100 witness report threshold, which defines a significant atmospheric entry in the AMS classification system. 5 such events stand in stark contrast to a historical baseline of roughly 2 per month. This places April on a trajectory for a rate 2.5 times the norm, almost the exact same elevated rate observed in March. We see 2 consecutive months, back to back, with the same high level of activity and no decay in between. Yet, as striking as the raw numbers are, the most critical part of the April picture is the timing of these events. If one examines when these major fireballs occurred, a crucial pattern emerges. The majority of them took place times after times, April 7th. They were not clustered in the first week of the month, when the M2026A1 stream was still technically within its predicted active window, nor did they fade out through the second week, as Earth moved past the stream's projected boundary. Instead, the events were distributed throughout the month in a way that showed no preference for the pre-closure period. They simply kept happening long after the window was supposed to have shut. It is this specific distribution that most cleanly shatters the explanatory power of the original stream model. To appreciate why, consider what a normal post-stream decay would look like in the data. If M2026A1 were the true driver of April's activity, and if that stream genuinely concluded on April 7th as predicted, the month's event distribution would have a characteristic shape. Activity would be high in the first week, while Earth was still near the densest part of the trail. It would become moderate in the second week, as our planet moved toward the stream's periphery, and low in the third and fourth weeks as we traveled well past its boundary. The AMS numbers for April would show a distinct downward slope, perhaps steep, perhaps gentle, but undeniably trending downward toward the background rate. What the data reveals instead is a shape that bears no resemblance to this expected decline. In the language of time series analysis, it shows a plateau, a sustained level of elevated activity that does not trend meaningfully downward as the month progresses past the closure date. A plateau is not just quantitatively different from a decay curve, it is qualitatively different. It tells a completely different physical story. A decay curve tells you that Earth is moving away from a concentrated region of debris, leaving the material behind as it journeys into cleaner space. The decreasing rate of encounters is a direct reflection of the decreasing density of the medium. It is simple geometry and predictable physics. A plateau, on the other hand, tells you something else entirely. It suggests that as Earth moves away from one concentration of material, it is simultaneously entering another of roughly the same density. The environment ahead is just as populated with debris as the environment left behind. The data suggests there is no simple return to normalcy, no clean exit into the lower density space that was expected to lie just beyond the meteor stream's boundary. What the observations show instead is a plateau. This occurs when an area of elevated density is not a localized stream with clear edges, but a much broader region. It points to a zone of space where the debris density remains consistently high, extending far beyond what any single stream model can explain. While single stream models are excellent at predicting decay curves, they do not account for plateaus. The M2026A1 model, for all its strengths, predicted a decay. The evidence, however, reveals a plateau. This is not a minor discrepancy that can be dismissed with error bars or uncertainty ranges. It is a fundamental, structural disagreement between the model's forecast and the unfolding reality. This picture becomes more concerning when we reintroduce the problem of geographic undercounting. The baseline rate for April noted as 2.5 times the norm, is a figure derived from AMS data. This number reflects events that generated enough reports on an English language platform used mainly by observers in North America and Western Europe. What this figure does not include is the Buenos Aires bolide, an event confirmed by multiple independent video systems and weather tracking, which still has 0 entries in the AMS database. It also omits any events over the 71% of our planet's surface covered by oceans. Furthermore, it fails to account for events in vast regions of Africa, South and Southeast Asia, and Central and South America, where reporting infrastructure is far less developed. The true global rate of significant atmospheric entries is therefore almost certainly higher than the official data shows. Just how much higher is a matter of genuine uncertainty. Researchers studying this bias estimate that real global rates are typically 3 to 4 times higher than observed rates. Under the current circumstances, with a confirmed major event over a massive city generating 0 database entries, that undercount factor could be even larger. This means the 2.5 times baseline is merely the floor. The ceiling remains unknown. Yet, there is a part of the April story that reframes everything else, and it is perhaps the most important aspect to consider. The M2026A1 model was not a failure. It is crucial to be precise about this point to understand our current scientific standing. The model did predict elevated activity for the period between March 16th and April 7th. And indeed, March was robustly and multidimensionally anomalous during that exact window. The orbital analysis by Schober correctly characterized a real debris stream from a real parent body using real data. The predicted radiant cluster was real, the timing was broadly accurate, and the proposed physical mechanism, sodium-driven fragmentation from a rock comet parent, was scientifically coherent. In the world of celestial mechanics, this represents a genuine scientific success, a rare achievement that deserves recognition. But this is where we must draw a critical distinction that shapes our entire understanding of the April situation. There is a profound difference between a model that is wrong and a model that is simply incomplete. A wrong model contains a fundamental error in its physics or its core assumptions. Its mechanics are broken, rendering its predictions unreliable. The solution is to identify the error, discard the model, and begin again. An incomplete model, however, is a different challenge. It may have the physics right for the portion of the system it describes, correctly characterizing one piece of a larger reality, but it has drawn its conceptual boundary in the wrong place. It has missed something fundamental, not because its internal science was flawed, but because the boundary itself was drawn too small. The M2026A1 model appears to be incomplete in precisely this way. Within its defined window, it performed admirably. The boundary it established, however, does not align with where the observed anomaly actually ends. Everything that has occurred beyond April 7th is happening in territory the model implicitly declared as normal. By ending its prediction there, the model suggested we would not need to explain anything further. For weeks, reality has been demonstrating that this line was drawn in the wrong place. An incomplete model can, in some ways, be more difficult to grapple with than one that is simply wrong. A wrong model offers a clean break. You discard it and rebuild. An incomplete model, by contrast, contains a mixture of valid information and unidentified gaps. You cannot simply throw it out, because the part it got right is genuinely valuable. Yet, you cannot simply extend it, because you do not yet understand what it missed or why. This leaves science in the uncomfortable position of holding a tool that is simultaneously correct and blind, without knowing where the boundary between those two states truly lies. This is exactly where we stand with M2026A1. It correctly described something real, but it did not describe everything that is real. The gap between what the model described and what April is showing us is the new frontier, the very place where the next explanation must be built. So we find ourselves in unexplained terrain. The data shows a plateau of activity that is undeniably real. The known undercount in reporting means the situation is even more significant than the numbers suggest. And now, a third stream of data, the Anthelian signal, hints that this terrain extends even further, and in directions the original stream model was never designed to look. This is where the investigation leads next. It is the piece of the puzzle that transforms the question from "when does this end?" to something far more unsettling. In the celestial sphere, there is a direction known as the Anthelian point. It is the spot in the sky directly opposite the Sun from Earth's perspective, the geometric anti-solar direction. As our planet moves through its orbit, it regularly sweeps up debris originating from this general area. This happens because objects in certain near-Earth orbits tend to intersect our path from that particular angle. The Anthelian source is a well-documented, diffuse contributor to the global fireball background. It is not a discrete stream from a single parent body, but rather a broad, directional tendency in the arrival geometry of background debris. In the first quarter of 2026, from January through March, the number of events attributed to Anthelian source radiance showed a startling increase. Compared to all previous records for that same period, the activity had roughly doubled. This unexpected surge from a background source adds another layer of complexity to an already profound mystery. Not a minor uptick, but a doubling of activity from the Anthelian source. This is profoundly important for understanding the recent surge, because this source, by its very nature, is not linked to any single, identifiable parent body. The distinction is critical. When a particular debris stream like M2026A1 is active, the fireballs it generates appear to come from a relatively concentrated point in the sky, a radiant tied to the stream's specific orbital path. An event's membership can be confirmed by tracing its trajectory back to that celestial region. Once the stream passes, those clustered radiants vanish. Anthelian events, however, behave differently. They originate from a wide, diffuse area of the sky that is a reflection of our own planet's motion through a background field of cosmic dust. Not tethered to a single parent or orbit, they measure the ambient density of debris that Earth encounters over long durations. A doubling of Anthelian events during the first quarter of 2026 cannot be explained by M2026A1. It is an entirely separate signal. It suggests the background, debris environment Earth was navigating was genuinely denser with material than is typical, not just in one direction, but across the broad anti-solar front our planet constantly sweeps through. To better visualize this concept, an analogy can be helpful. Imagine the difference between driving through an isolated, intense rainstorm versus traveling through a large region characterized by persistently high humidity and a general tendency for precipitation. That intense but temporary rainstorm is the M2026A1 stream. It is localized, and you will eventually pass through it. The elevated regional humidity, however, represents the Anthelian signal. It is diffuse, directional in a broader sense, and much more persistent. While you can drive out of the storm, you cannot so easily exit the entire humid region. If this heightened Anthelian activity truly reflects a greater debris density in the part of the solar system Earth is now crossing, then the conclusion of the M2026A1 encounter does not signal an end to the increased risk. It would simply mean the dominant, localized source has passed, while the broader, more hazardous environmental conditions remain. We may not be merely crossing a stream. It is possible we are now moving through a sector of the inner solar system that contains far more material than our models had ever predicted. This carries profoundly different implications than the single stream model. If it is a stream, one simply waits for it to pass. But if it is a region, the question becomes far more daunting. How vast is this region, and for how long will we be inside it? The Anthelian data from Q1 suggests this denser environment may have been developing for some time before the March spike, raising a truly unsettling prospect. What if the events of March were not an isolated spike, but merely the most intense phase of a much longer encounter with a poorly mapped debris zone? This would mean that April's plateau is not the fading tail of that spike, but the new baseline of a sustained environmental condition. We will explore that idea in greater detail in the second half of this program. But first, we must examine the global distribution of events during this period, as the geographic spread adds another critical layer to this unfolding story. If all the heightened fireball activity originated from a single, well-defined debris stream, we would expect a very specific pattern of where the impacts occur. A discrete stream possesses a distinct geometry, and Earth intersects it at a particular angle from a predictable direction. The debris arrives from a specific radiant, and because our planet rotates at approximately 15 degrees per hour, different longitudes on Earth face that radiant at different times. A stream with this well-defined geometry should therefore produce an event distribution that appears preferentially over the parts of the globe facing the correct direction at the correct time. The mathematics are precise, and the geometry is traceable. Yet, what the April data reveals is something else entirely. We see events recorded over South America, others over Western Canada, and still more across the Central Pacific, all scattered across multiple continents within just days or weeks of each other. This wide geographical spread is a significant problem for the single-stream hypothesis. When we examine the available radiant data for the confirmed April events, those few that have been properly analyzed, the picture is not one of a tight cluster pointing back to a single origin. Instead, it shows a noticeable spread. This dispersion is consistent with the Anthelian interpretation, which allows for multiple radiants or a diffuse source. However, it directly contradicts the M2026A1 model, which had specifically predicted a tight radiant cluster within the Virgo-Corvus-Libra region of the sky. The Schober model's radiant prediction was one of its most important features, its claimed ability to tell us not only when events would happen, but from which direction in the sky they should appear to come. If the fireballs after April 7th were merely tail-end activity from M2026A1, they should share that same radiant cluster, which the available data does not confirm. So, what could be causing a distribution so much broader than our models anticipated? There are a few possibilities to consider. First, it is conceivable that multiple debris streams are active at the same time, with overlapping encounter windows and different radiants, producing a composite pattern that only appears to be diffuse. Second, there might be a genuinely diffuse source, a vast cloud or region of debris, rather than a discrete stream, whose geometry would naturally result in events arriving from a wide spread of apparent origins. A third possibility is that our analysis of the radiance is simply incomplete, as we are working with data from only a small fraction of events that were properly logged and studied. But all three of these possibilities ultimately lead to the same conclusion: the M2026A1 model, even if its fundamental mechanics are sound, is not sufficient on its own to explain the full pattern of what is being observed. The spatial distribution of events is simply too broad. The activity has persisted for too long. The Anthelian signal is too strong and appeared too early, and the activity continuing after the main window cannot be dismissed as mere statistical noise. The central question remains the same: what, precisely, is Earth flying through? But the global distribution data sharpens the answer. We are not just navigating the fading trail of a single comet-like object. Whatever this is, it is bigger, more diffuse, and it does not conform to the boundaries set by our models. This brings us to the model itself, because to comprehend where it may have failed, we must first appreciate just how impressive its predictions were. In the field of near-Earth space science, researcher Patrick M. Schober accomplished something genuinely rare with his analysis of the M2026A1 anomaly. He moved from a fresh observation to a testable prediction with remarkable speed, assembling data from multiple independent networks to apply rigorous orbital mechanics. This is science in action, moving from mystery to hypothesis in time for the results to be meaningful. His work was grounded in a substantial data set for this type of investigation, drawing upon 282 separate meteor detections. These were collected by coordinated global monitoring systems, including the French-led FREEPON network and the Global Meteor Network, which compiles data from camera stations across dozens of countries. These networks operate continuously, capturing meteor events with standardized, calibrated instruments. This allows scientists to process the data, to reconstruct a meteor's trajectory, calculate its brightness, and sometimes even determine its orbit before it entered our atmosphere. While this system isn't perfect, coverage remains geographically uneven, and smaller events can go unnoticed. It represents the most systematic capability for monitoring near-Earth debris available to the public scientific community. Within this wealth of data, Schober identified a coherent stream, a population of meteoroids sharing orbital characteristics that pointed to a common origin, spread along a single track. His proposed source for this debris was a fascinating object known as a rock comet. To appreciate the significance of this, it helps to understand the celestial classifications. The cosmos rarely fits into neat boxes, and the distinction between asteroids and comets is a prime example. Most are familiar with asteroids as rocky, largely inert bodies that do not produce tails or significant outgassing. Comets, by contrast, are rich in ice and volatile compounds. When they approach the sun, solar heating causes their surfaces to erupt with gas and dust, creating spectacular tails and scattering debris along their orbits. In fact, the predictable annual meteor showers we see, like the Perseids and the Leonids, are the result of Earth passing through the debris trails left by periodic comets. Rock comets, however, occupy a compelling middle ground. They are predominantly rocky, more akin to asteroids, but they possess certain mineral components that react to solar heating with measurable outgassing or fragmentation. The most studied example is the asteroid 3200 Phaethon, which is linked to the annual Geminid meteor shower. Phaethon's orbit brings it so close to the Sun that the intense heat is thought to vaporize sodium and perhaps other materials from its surface, producing a faint, comet-like behavior. It is a rocky body, not an icy one, yet it sheds mass near its closest solar approach, seeding its orbit with debris. The model proposed for M2026 A1 relies on this very same mechanism, sodium-driven fragmentation. The theory suggests that as the parent body makes repeated close passes by the Sun, its sodium, which has a relatively low vaporization point, is heated and driven from the surface. This process would gradually fracture the object, distributing fragments of material along its orbital path. Over time, this debris spreads out. When Earth's own orbit intersects that track, we experience the meteor events observed in March and early April. The beauty of this model lies in its simplicity. It doesn't rely on exotic physics, but instead uses a mechanism already demonstrated in other known rock comet systems. Crucially, the hypothesis made a precise prediction and underwent the scrutiny of peer review, where it was deemed credible enough for publication. In a landscape where discussions of fireball anomalies often remain in informal online forums, a peer-reviewed paper presenting 282 detections and a specific orbital model represents a genuine scientific achievement. However, as solid as this foundation was, the model was also incomplete, and it is vital to understand the nature of that incompleteness. The active window predicted for M2026A1 was from March 16th to April 7th. These dates were not approximations or a vague range. They were specific calculations derived from the laws of orbital mechanics. The model determined exactly when Earth would enter the debris stream's path and how long it would take our planet to cross it at its orbital velocity. This precision is both the model's greatest strength and, as we will see, the source of its greatest challenge. When properly applied, orbital mechanics is an exceptionally precise science. The model wasn't simply suggesting elevated activity in the spring. It was making a firm statement that this activity would occur between two specific dates and then cease. It is this very precision that makes the events occurring after the window so profoundly significant. If the model had predicted a period of heightened activity during the spring of 2026, with an uncertainty of several weeks, then the fireballs appearing in late April could have been accommodated within that margin of error. One could argue the timing was still broadly consistent with the model, but that is not what the model stated. It provided a clear cutoff date, and the events that followed 20 to 22 days later are far outside any reasonable uncertainty for a model of this precision. Then, this is where a successful prediction becomes a new and compelling mystery. The discrepancy demands an explanation, forcing us to re-examine the initial assumptions. To understand why the model was so precise, it helps to visualize how debris streams behave in space. A stream is not a diffuse, fuzzy cloud. It is a defined orbital track, a specific path through the solar system dictated by the parent body's original orbit. While debris does spread along that track over time due to slight differences in ejection velocity and other perturbations, the main concentration of material remains tightly bound to that original path. Earth intersects this track at a specific angle, over a specific distance, and at a specific velocity. This geometry is so well defined that it yields a window of encounter measured in days, not months. If Earth entered the stream on March 16th and exited on April 7th, the cross-section of that stream was equivalent to about 3 weeks of our planet's orbital travel. This provides a physically meaningful constraint on the stream's dimensions. When events continue to occur 20 days after Earth should have cleared that geometry, the possibilities are limited. Perhaps the stream was wider than the model accounted for, or maybe there is additional, separate debris outside the mainstream. It is also possible there is another source entirely, or some combination of these factors. What the precision of the model provides is not a vague inconsistency, but a precise failure, a clean, measurable gap between prediction and observation. A precise failure is often more scientifically valuable than a vague success, as it clearly points to where our understanding is incomplete. As of now, that gap in understanding remains. There is no peer-reviewed paper extending the M2026A1 model to account for these later events. No alternative stream has been identified. There is no published explanation for why the skies of late April looked the way they did. The model worked perfectly until the moment it didn't, and in that fascinating gap, a new investigation begins. It is often at the point of failure that a scientific story reveals its most profound secrets. Our story now arrives at such a moment in its 11th part, the failure of the model's closure window. When we speak of the model failing after April 7th, we are not describing minor anomalies. This is not a matter of 1 or 2 stray events that could be dismissed as statistical noise. Instead, we are faced with a persistent and unmistakable signal, a sustained pattern of elevated activity, with the impact rate holding at 2.5 times the baseline for the entire month. This occurred during a period when the model insisted that activity should have returned to normal. The deviation is not subtle. The Buenos Aires event on April 27th arrived a full 20 days after the model's closure, and the British Columbia event on April 29th followed. 22 days passed. In the context of orbital mechanics, these are not borderline cases. They are far outside the predicted zone of activity, raising fundamental questions about what the model missed. To understand the implications, we must first draw an important distinction between a model that is broken and one that is merely incomplete. A model that breaks down is built on a fundamentally wrong assumption. Something within its core mechanics is incorrect, meaning the predictions it generates are invalid because the underlying physics was misunderstood. This represents the most alarming kind of model failure. An incomplete model, by contrast, may have its physics right for the part of the system it describes, but has simply failed to include all of the relevant components. In this second scenario, the model's predictions are correct for the part of the story it tells, but there is more to the narrative than it was able to capture. The case of M2026A1 appears to be a clear example of this latter situation. The predictions for March were, by and large, correct. The stream was real, the radiant cluster appeared where expected, and peak activity occurred roughly when the model said it would. But the model evidently did not account for something else. This missing piece could be a debris tail that extends much further than the main stream, an overlapping secondary source, or perhaps an anthalon contribution that amplifies the background rate. The core science does not seem to be wrong, but its boundaries were drawn too narrowly. This distinction is not just academic, it determines the entire course of the scientific response. If a model is fundamentally broken, the only logical step is to discard it and begin the difficult process of starting fresh. But if a model is correct yet incomplete but bounded, then the task becomes one of extension. Scientists can then ask what it missed, using the new data from beyond the predicted window to try and reverse engineer the structure of the debris field they are apparently still traveling through. As of now, that difficult work has not been completed. The only peer-reviewed explanation for the spring 2026 surge from the excellent work of Schober concludes its analysis on April 7th. The ongoing anomaly has now clearly outgrown its explanation. It is important to note that this is not a criticism of that foundational science, which was rigorous and based on all data available at the time. It is simply a statement about where the science now stands in relation to the unfolding reality the data is revealing. The old map has led us to the edge of a new, uncharted territory, and we must consider how to begin charting it. In this 12th part of our analysis, we can explore 3 ways to potentially save, or rather extend, the model. The first is the extended debris tail hypothesis. Debris streams do not have hard edges. While the densest region produces the peak activity, a diffuse periphery of older debris surrounds this core, spread out over millennia by forces like the Poynting-Robertson effect and radiation pressure. Earth could now be passing through this faint outer edge of the M2026A1 field. The strength of this idea is its elegance. It uses the same physics as the original model. Its weakness, however, is that it struggles to explain the spatial distribution of recent events. If these impacts were from the stream's outer fringe, their radiance should still be broadly consistent with the stream's geometry, but the wide geographic spread in April suggests this is not the complete answer. A second possibility is the multiple source hypothesis. This theory posits that while the March surge was dominated by M2026A1, the continued activity in April reflects one or more additional, uncharacterized debris streams. These hypothetical streams could be overlapping in time with the tail end of M2026A1, creating the appearance of a seamless continuation. This hypothesis neatly explains the broader radiant distribution, as multiple sources would naturally produce multiple radiants. Its weakness is that it requires undiscovered streams significant enough to maintain an impact rate 2.5 times the baseline. This implies substantial debris populations near Earth that our detection systems have not yet found a deeply uncomfortable possibility. There is a third, more introspective option: to accept the limitations of our incomplete modeling. This is an acknowledgement that the tools we currently possess are not yet capable of producing complete models of such complex, multi-component debris fields. From this perspective, the model was as good as it could be, but reality proved far richer than it could capture. This view doesn't require a specific alternative mechanism. It is an acceptance that we have reached the frontier of our current modeling capability. The profound weakness here is that this is not an actionable path forward. One cannot extend a model whose gaps are not understood. While it may be the most honest assessment, it offers little in the way of predicting what comes next. When we weigh these three approaches, none of them, on its own, can simultaneously explain all the features we are observing. The broad distribution of impacts, their temporal persistence, the perplexing anthalon signal, and the global undercount, all these pieces of the puzzle remain. Putting them all together seems to require something more than any single extension of the existing model, and that points toward a possibility we will explore in our final act. This suggests we are not merely witnessing the tail end of a known meteor stream, but are instead passing through a volume of space that is fundamentally more crowded with debris than our long-term models of the inner solar system have led us to believe. But before exploring that possibility further, we must address something that underpins everything we have discussed. It is a fundamental truth about how we observe the space around our planet, and more importantly, what we consistently fail to see. This is brought into sharp focus by a recent asteroid story that deserved far more attention than it received. A small asteroid, approximately 5 meters in diameter, recently passed by Earth. It flew beneath the ring of geosynchronous satellites, placing it closer to our world than the craft that provide our GPS signals and television broadcasts. And no one saw it coming. Let that reality settle in for a moment. An object from space moved through the near-Earth environment, passing between our planet and our own vital infrastructure, without any prior detection. The first confirmation of its existence came only after it had already sped past us. This event raises a critical question about the true state of our cosmic neighborhood. In astronomical terms, a 5-meter object may not sound like a significant threat. It is, after all, just a boulder, not something that could trigger a planetary catastrophe. But when viewed in a different context, its potential danger becomes clear. An object of this size belongs to the same class as the bolides that are capable of producing meteorite falls on the surface. We can look to events like the Chelyabinsk meteor of 2013 for reference. That object was estimated to be around 20 meters. Yet the forward scattered blast from its atmospheric entry injured over 1,400 people and caused widespread structural damage across a region of Russia. A 5-meter object entering our atmosphere at typical impact speeds would unleash energy equivalent to between 100 and 1,000 tons of TNT. That is more than enough to cause significant local damage if it were to strike a populated area. And an object of this very class passed inside our satellite ring, completely unannounced. This is not a hypothetical risk. It is a documented occurrence. The reason this happened is not due to a failure at any single telescope or observatory. Rather, it is a direct consequence of the fundamental architecture we have established for monitoring near-Earth space. Our capabilities for detecting asteroids have been optimized to find large objects. A program known as the SpaceGuard Survey was tasked with locating objects larger than 1 kilometer, the kind that could inflict damage on a continental or even global scale. Today, the catalogue of these massive bodies is reasonably complete. We have successfully identified the vast majority of near-Earth asteroids above that size threshold, and we can say with confidence that none of them pose an impact risk in the near term. At the most catastrophic end of the scale, this is genuinely reassuring news. However, the picture changes dramatically as we look at smaller objects. For an impactor measuring around 140 meters, the result would be regional devastation, capable of destroying anything from a city to a small country, depending on its trajectory. At this size, our catalogue is estimated to be only 40 to 50% complete. For every one we have found, another may be lurking out there, its orbit entirely uncharacterized. And when we consider objects smaller than 10 meters, the category that includes both the recent Earth-grazing asteroid and the fireballs we have been tracking, the catalogue is essentially empty. These bodies are simply too small, too numerous, and too dark to be reliably detected by current survey telescopes before they approach Earth. They only appear in our databases when they burn up in the atmosphere, or when they pass so close that they are picked up by chance during a survey sweep that just happens to be pointed in the right direction at the right time. This reality creates a profound and largely unacknowledged disconnect at the heart of near-Earth space science. On one hand, we have excellent data on what is happening within our atmosphere. The fireballs we are discussing are real and meticulously tracked. On the other hand, we have almost no data on what is approaching the atmosphere until the moment it arrives. The 2.5 times baseline fireball rate in March and April of 2026 is telling us that something real is occurring. Yet we cannot tell you right now what is currently on a trajectory toward Earth in the 5 to 20 meter range. We have no idea, not because of a specific failure, but because these objects are systematically below our detection floor. If we are indeed moving through a denser than expected field of debris, which is the hypothesis that the persistent activity forces us to consider, then the population of undetected incoming objects in that size range is correspondingly higher than our models predict. The 5-meter asteroid that buzzed Earth without warning is not an anomaly. It is a sample, a single data point from a much larger distribution of objects that we are simply not seeing. This connects the detection problem directly back to the central theme we have been building. The gap between our models and reality is not just about scientific theory. It is about what our entire detection architecture was built to find and what it consistently misses. To understand this better, it helps to think of near-Earth asteroid detection as a fishing net with a mesh of a certain size. Everything larger than the mesh gets caught, while everything smaller slips through. Our current net is reasonably effective at catching the large, dangerous objects. The 1 kilometer and larger asteroids that could end civilization are mostly accounted for. The net catches medium-sized objects in the 100 to 140 meter range inconsistently. But for anything smaller than about 10 meters, a range that covers all the fireball events we have been discussing, the net is essentially open water. These objects pass through our observation systems without a trace until they arrive. The reasons for this are well understood. Small asteroids are dark, possessing a low albedo, which means they reflect very little sunlight and are difficult to see against the black backdrop of space. A 10-meter rock at a distance of 50,000 kilometers is extraordinarily hard to detect, even with our most advanced survey instruments. Its rapid angular motion across the sky makes it challenging to distinguish from artifacts in the data. The window of detectability, the brief period when it is close enough to be bright enough and in the right orbital position to be seen, may last only for a few hours or days before its closest approach. Our current telescope networks were neither designed nor funded to survey the entire sky fast enough to reliably catch these small, swift-moving objects. On top of all this, there are also geometric blind spots that make the task even harder. Certain objects that approach our planet are rendered effectively invisible to us. These impactors, sometimes called sun grazers, arrive from the direction of the sun, a region of the sky where the intense glare makes it impossible for ground-based optical telescopes to observe. This creates a fundamental blind spot in our planetary defense systems. The most difficult events to detect in advance are these daytime impacts and near misses originating from the solar direction. The Chelyabinsk event was a stark reminder of this vulnerability. It approached from a low solar angle and was not detected before impact, which is why it took the world by such complete surprise. This inherent detection flaw casts a new light on the fireball anomaly we have been exploring. The events at the heart of this discussion, the Buenos Aires bolide, the British Columbia fireball, and the April cluster, all involve objects estimated to be in the 5 to 20 meter size range. These are precisely the kinds of objects that fall beneath our current detection capabilities. We only learn of their existence because they enter our atmosphere and incinerate. What we cannot know is how many companions they may have had. Similar-sized objects, on slightly different trajectories, part of the same stream of debris, have not yet crossed Earth's path. We are unable to count them because we cannot see them. This places us in a uniquely challenging position. We are forced to study a population of objects based solely on its effects, the frequency and characteristics of fireballs, without being able to survey the population directly to measure its size, density, or true extent. It is akin to mapping a storm by noting only where the raindrops land, with no instruments to see the clouds themselves. If the surge predicted for spring 2026 is indeed an encounter with a denser than expected debris field, then the fireballs we can detect are merely the signal. The vast number of undetectable companions, those objects that miss Earth or have yet to arrive, represent a background noise we cannot quantify. The gap between what we observe and what truly exists could be far larger than our known geographic reporting biases already suggest. Our systems are designed to detect the rare, large impactors, but we consistently miss the far more frequent small objects, and at this moment, these smaller objects are appearing in numbers that our best models cannot explain. This means we are navigating through a region of space that appears more populated than our maps predicted, using instruments with a known structural blind spot. A simple, powerful fact frames every conversation about fireball rates and impact risk. 71% of our planet's surface is covered by ocean. This number is profoundly relevant, yet it is almost never mentioned in summaries of meteor activity. When we discuss the frequency of fireballs, we are almost always talking about times reported times fireballs. A reported event is one that was witnessed by a person or captured by an automated, land-based camera network. A fireball that streaks across the sky over the South Pacific at 4 in the morning has no human witnesses. There is no camera network beneath it, and no established pipeline for reporting. It enters the atmosphere, burns with spectacular intensity, deposits its energy, and vanishes without a trace. The only way such an event ever makes it into a database is if a weather satellite with the right sensitivity happens to be looking at the right patch of sky at the right moment. This does happen occasionally, but it is far from systematic coverage. The American Meteor Society database, which has been our main source for analyzing the spring 2026 surge, is subject to this same limitation. Its data is concentrated in regions where English-speaking skywatchers gather in significant numbers, primarily the continental United States, Canada, the United Kingdom, and parts of Western Europe. Consequently, South America is undercounted. Africa is dramatically undercounted. Central and Southeast Asia are also undercounted. And the vast ocean surface, covering most of the Earth, is essentially a void in the data, aside from those chance detections by satellites, not designed for this task. The practical effect of this geographic bias is significant. Researchers who study the relationship between reported and actual fireball rates consistently estimate that the true global rate is roughly 3 to 4 times higher than what is observed. Not 10% or 50% higher, but 300% to 400% higher. This implies that if we are observing a rate 2.5 times the baseline in the regions we monitor, the actual global rate might be closer to 6 or 8 times the baseline. We genuinely do not know. What we do know is that the Buenos Aires event fits this pattern of underreporting perfectly. It occurred over one of South America's most populous urban centers, an area with excellent infrastructure and widespread camera coverage, yet it still failed to enter the primary fireball database. Let that sink in for a moment. If that is the fate of a fireball over Buenos Aires, what happens to one over the central Amazon basin, the Bengal Current off the coast of Southwest Africa, or the Tasman Sea? These are not hypothetical challenges. They are real geographic areas experiencing real atmospheric events that leave no record in any scientific database. The Buenos Aires gap is not an isolated failure. It is a representative example of a systematic undercount that affects our entire understanding of what is happening in the skies above us. And as we try to determine the accuracy of the M2026A1 model, we are working with a dataset that may be missing the vast majority of the events that could provide an answer. So, the surge may be significantly underestimated. The geographic blind spots compound the problem of our detection threshold, and layered on top of both issues, the data itself has quality problems that must be acknowledged. The Center for Near-Earth Object Studies, or CNEOS, is NASA's primary fireball database. It is the most official-sounding reference for high-energy atmospheric entries, cited in news articles and scientific papers as the authoritative source for significant bolide events. It carries immense institutional weight. However, it also has known accuracy problems, particularly for smaller events. There have been documented cases of coordinate errors in CNEOS data, with reported locations being off by hundreds or even thousands of miles from where the event actually occurred. The most notable case involved an event that was mislocated in the database by approximately 1,800 miles, a staggering degree of error for what is considered an authoritative record. The problem with our data is not some minor calibration offset, a small error of a few dozen kilometers that might be expected from the limits of infrasound triangulation. Instead, we are facing potential mislocations on a continental scale. This accuracy issue is most pronounced for smaller impacts, specifically those with an estimated energy below 0.45 kilotons, which corresponds to objects less than a few meters across. For more powerful events, the impact location is typically constrained with greater accuracy by multiple independent systems, such as infrasound, seismometers, and optical satellites. At lower energies, however, an event might only be registered by one or two systems, leading to much larger geometric uncertainties. This presents a fundamental challenge, as the current surge in activity is composed almost entirely of events within this lower, less accurate range. The fireballs we have been tracking are mostly from subkiloton objects, whose atmospheric entries release energy far below the CNEOS accuracy threshold. This means that even the most official datasets for these events contain a degree of locational uncertainty that could place an impact hundreds of miles from where it actually occurred. Such data is not particularly useful for detailed trajectory analysis, nor is it reliable for comparing event locations against predicted radiant distributions. It is certainly not reassuring when trying to determine if the post-window activity is concentrated in a region consistent with a meteor stream's geometry. This does not render the CNEOS data useless, but it demands that we use it with caution, cross-validating it and acknowledging its limitations. The precision implied by a specific latitude and longitude in the database may not reflect the true precision of the measurement. In our current context, this means that the geographic analysis needed to test for an association with the M2026A1 stream is severely hampered by data that was never intended for this level of scrutiny. Every layer of this data problem seems to point in the same direction. The geographic coverage is biased, reporting rates are inconsistent, and the official databases have well-documented accuracy issues for small events. The entire system is operating under anomalous conditions for which it was never specifically designed, struggling with a phenomenon that has outgrown our best models. What we are left with is the best available picture of an incomplete reality. And yet, even within this imperfect picture, something is clearly inconsistent with the assumption that the spring 2026 surge concluded on April 7th. This leads us to the most difficult question of all. What are we actually flying through? Part 17. Extended stream versus overlapping systems. Fundamentally, there are two families of hypotheses to explain what Earth is currently moving through, each with different implications for what may come next. The first family of theories suggests this is still primarily about the M2026A1 stream. In this view, the stream is real and was correctly characterized, but its physical extent is simply larger than the initial model captured. While the core of the stream that produced the March peak was mapped accurately, meteor streams do not end abruptly like a closing door. They thin out gradually over vast distances. The tail of M2026A1, composed of lower density debris outside the main orbital path, may extend significantly further than the observational data could constrain during the modeling process. If this is true, Earth is still moving through this tail, which, while less dense than the core, is still more concentrated than the background environment. And because we know from the Buenos Aires analysis that our reporting systems miss a significant number of real events, the tail's true density is likely higher than the database numbers suggest. The elegance of this hypothesis lies in its simplicity. It uses the existing model, extends it in a physically plausible way, and does not require invoking any new sources or mechanisms. Its primary weakness, however, is that it does not offer an obvious explanation for the Anthelian signal. The observed doubling of activity from the Anthelian source points to an elevated flux from a direction not associated with M2026A1's radiant cluster. It is difficult to fit the Anthelian data into a single stream tail hypothesis without seriously compromising the model's coherence. The second family of hypotheses proposes that there are multiple overlapping sources. In this scenario, M2026A1 explains the activity in March and early April, but one or more additional, uncharacterized streams are contributing to the ongoing events. These could be streams from different parent bodies, perhaps rock comets, or asteroid families, with orbital resonances that bring their debris to an Earth-crossing geometry during the same spring window. Alternatively, they could be dynamically related fragments of a much larger parent object that broke apart and scattered debris across a range of different orbits. This multi-source hypothesis naturally explains both the Anthelian signal, which would represent a separate source with a different radiant geometry, and the persistent post-window activity. Its weakness is what it implies about our understanding of the solar system. It requires the existence of significant, uncharacterized debris sources, which means either that our surveys have missed something substantial, or that these sources are new, perhaps created by a recent fragmentation event that we have not yet identified. There is also a hybrid possibility that sits between these two families of thought. We may be traveling through a genuinely diffuse debris environment that is not organized into discrete streams at all, at least not in the way our models are designed to characterize them. This would be a zone of relatively higher small body density in the inner solar system, shaped by some combination of historical fragmentation events, gravitational resonances delivering material from the main asteroid belt, and cometary dust contributions. Our orbital surveys may have systematically undersampled this environment because it is populated by objects below our detection floor. Evaluating which of these scenarios is closest to the truth is the work that needs to happen now. At present, it is not being done, at least not publicly, and certainly not at the pace the data demands. The post-window events have continued to accumulate to the point where the question has become urgent. We need new models, and we need the observations to constrain them. Part 18. Burns 3. Factor Framework. A researcher named Stephen Burns has proposed a framework for thinking about why near-Earth debris encounter rates might be increasing, and it is worth engaging with seriously. His perspective is compelling because it does not rely on any single anomalous stream or unusual parent body. Instead, it is a systemic argument seeking a broader cause for a changing environment. To truly grasp the fluctuating rates of fireballs we observe, researcher Burns proposes we must consider three distinct but interconnected factors. The first of these is Earth's own journey through the solar system. Our planet travels at approximately 30 kilometers per second, but the heliocentric debris field it navigates is far from uniform. This cosmic environment is a complex tapestry woven with gravitational resonances, the ancient paths of comets, and the scattered remnants of asteroid collisions. These forces create zones of high and low density. As Earth follows its annual orbit, it predictably passes through these denser sectors, which helps explain why certain times of the year see more activity. This perspective transforms our view, suggesting that what seems random is often a consequence of our planet's predictable path through a structured environment. The second factor expands our perspective from the solar system to the galaxy itself. Our entire solar system is hurtling around the center of the Milky Way at a staggering 240 kilometers per second. Over millions of years, this journey takes us through interstellar regions of varying density. On timescales more relevant to our present moment, the solar system's orbit causes it to periodically cross the galactic plane, the densest part of the Milky Way's disk. Some researchers link these crossings to periodic increases in comets being sent into the inner solar system. While this is a very long-term cycle, it could establish a background level of activity that influences the encounter rates we experience over shorter periods. It's a reminder that our local environment is nested within much larger cosmic rhythms. The third and final factor brings our focus back to our own cosmic neighborhood, the mechanisms that deliver asteroids toward Earth. Gravitational resonances with Jupiter and other gas giants have created escape hatches within the main asteroid belt. These are regions where orbital dynamics become unstable over thousands to millions of years. When objects drift into these resonant zones, they can be flung onto highly elliptical orbits that cross Earth's path. The population of near-Earth objects we see today represents a delicate balance between this delivery process and the rate at which these objects are destroyed or ejected. This raises a critical question. If a recent collision in the asteroid belt has fed a new supply of material into these gravitational pathways, we could be experiencing an elevated delivery rate that might persist for thousands of years. The power of this three-part framework is its ability to explain the variability without resorting to a single extraordinary event or a mysterious new meteor stream. Instead, it presents these fluctuations as a natural consequence of Earth's position within a complex, multi-layered gravitational system. However, this perspective also leads to a rather sobering prediction. If our planet is currently passing through a period of naturally higher debris delivery driven by our galactic position, asteroid belt dynamics, or a combination of both, then the increased encounter rates we are witnessing may not be a temporary spike. It might not be an anomaly that will simply fade away, but rather the emergence of a new, slightly higher baseline that will persist until the underlying cosmic conditions shift once more. The primary challenge with this model, however, is its testability. The processes it describes unfold over immense timescales, from thousands to millions of years. Attempting to directly link these long-cycle phenomena to a specific 2-month anomaly observed in 2026 is fraught with enormous uncertainty. The framework provides a compelling reason for why elevated rates are possible in principle, but it cannot definitively explain why they are happening at this exact moment and with this specific intensity. It gives us a map of possibilities, but struggles to pinpoint our exact location on it. Yet, the framework succeeds in shifting our line of questioning in a crucial way. Instead of asking only, why is there a spike, and when will it end? We are prompted to consider a more fundamental question. What is the new baseline, and by how much has it shifted? These two questions are not the same. They lead to vastly different answers and carry profoundly different implications for everything, from planetary defense and near-Earth space monitoring to our fundamental understanding of the risk environment our world inhabits. This leads us to an uncomfortable but essential hypothesis, one that seems to be hiding in plain sight within the data. What if the number of small Earth-crossing objects, those in the 1 to 2 0-meter range, too small for our primary detection systems, but larger than typical meteor dust, has been steadily increasing for years? It is possible that we are only just now becoming aware of this change, because the cumulative increase has finally crossed the sensitivity threshold of our reporting systems. This is not a prediction of imminent disaster, but rather a hypothesis about a fundamental shift in our background environment. If this hypothesis is correct, it would simultaneously explain several puzzling observations that models focused on specific streams struggle with. It would account for the doubling of anthelian fireballs in the first quarter, which points to an elevated density of debris coming from a broad direction, not a narrow, defined stream. It would also explain why March was anomalous, across so many different metrics at once, not just the frequency of events, but also their size distribution. The rate of sonic booms, duration statistics, and the spread of their radiance. A genuine increase in the background population of small impactors would naturally produce precisely this kind of widespread, multifaceted anomaly. Furthermore, this idea would clarify why fireball rates in April did not return to their previous baseline. If the entire background population is elevated, then every month should appear somewhat elevated, not just the months associated with a known meteor stream. It also provides a compelling explanation for why the M2026A1 model was accurate within its specific time frame but failed outside of it. The model likely identified a concentrated stream, a wave moving through an ocean where the tide itself was already unusually high. So, what could trigger such a genuine increase in the population of small Earth-crossing bodies? Several physical mechanisms could be responsible. Among the most plausible are recent fragmentation events, where collisions within the main asteroid belt or among existing near-Earth objects have generated a fresh supply of debris. This new material could then be injected into orbits that bring it into our planet's path, subtly but steadily changing the nature of our cosmic environment. When we witness an unusual pattern in the cosmos, the first question is always, what is the cause? One possibility lies in the asteroid belt, where immense collisions between large bodies can occur. These are not continuous events, but rather rare impacts happening on timescales of hundreds of thousands to millions of years. Such a collision would produce a cascade of fragments, with some pieces drifting into resonant orbital zones that eventually guide them toward the inner solar system. If a significant impact took place in the relatively recent astronomical past, this delivery chain could be feeding an elevated flux of small bodies into our neighborhood right now. Another mechanism involves the slow, gravitational dance of the planets, which can gradually alter the resonance structure of the asteroid belt over eons. These subtle shifts could be delivering material to Earth-crossing orbits at a rate higher than what was typical just 1,000 years ago. A reminder that the solar system is a dynamic, evolving place. Earth's own geological impact record confirms that these delivery rates are not constant. A third scenario, currently speculative but plausible, suggests the recent breakup of a near-Earth asteroid or a short-period comet. This event could have spread debris along a path that extensively overlaps with our own planet's orbit. It would not be a single, discrete stream like M2026A1, but rather a complex of several overlapping streams, all originating from the same fragmentation. This would create a vast zone of heightened debris density, one that Earth might travel through for weeks or even months of its annual journey. These are not concepts from science fiction. They are all real, physical processes known to operate in our solar system. The pressing uncertainty is whether any of them are currently active enough to explain what we are observing. To even begin to answer that, we must first acknowledge a difficult truth. The current data pattern, a sustained rate 2.5 times the baseline for 2 consecutive months, persisting beyond the expected window, and distributed broadly across the globe, is inconsistent with our prior models of what normal should look like. This raises the uncomfortable possibility that normal itself has shifted, and that we have entered a period of genuinely elevated debris activity not from a single stream, but because the very environment we are moving through has changed. To understand the stakes, we must first establish a sense of scale, where precision matters far more than drama. The fireball events that have captured our attention are largely caused by objects in the 1, 2, 5 meter size range, with the most energetic of the April events perhaps reaching up to 10 meters. At these dimensions, an atmospheric impact is a localized spectacle. It is dramatic and potentially damaging if it occurs directly over a populated area, but it is not regionally catastrophic. Consider the Buenos Aires bolide. Had it penetrated deeper into the atmosphere and detonated over the city center, it would have produced a blinding flash and a powerful pressure wave. The result would have been sonic damage, broken windows, and frightened citizens. It would have been major news, but it would not have been a disaster on the scale of a nuclear weapon or a major earthquake. This context is crucial. We are not observing an existential risk unfolding in real time. However, the significance of these events lies not in their individual power, but in what they represent about the broader population of near-Earth objects. Small impacts are merely the visible tip of a size-frequency distribution that extends to much larger bodies. For every 1 0-meter object that enters our atmosphere, statistics suggest there are somewhere between 10 and 150 objects in that same family, measuring 50 meters across. An object in that 5 0-meter class is comparable to the one responsible for the 1908 Tunguska event, which flattened approximately 2,000 square kilometers of Siberian forest purely from its airburst, without leaving an impact crater. These are the objects we do not see coming. We do not catalogue them, nor do we track their orbital parameters. They exist within a critical detection gap that our current planetary defense architecture was not built to close. History provides us with sobering case studies. In 2013, the Chelyabinsk meteor, an object roughly 20 meters in diameter, exploded over a populated Russian region. It was not detected in advance. The blast injured over 1,400 people and caused widespread structural damage. That event arrived without any warning, on a morning when the world's astronomical attention was ironically focused on a different known asteroid that was making a safe, scheduled, close approach on the same day. We were watching the object we knew about, and we completely missed the one that was actually arriving. Decades earlier, the 1908 Tunguska event involved an object estimated at 30 to 60 meters. Its composition remains unknown, as it burst completely in the atmosphere, yet it devastated a remote forest area equivalent in size to a major metropolitan region. Had its entry geometry been slightly different, causing it to detonate over London, Paris, or St. Petersburg, it would have been recorded as one of history's worst disasters. These are not hypothetical extremes. They are recent events in geological terms, and they occupy the size class just above the fireballs we are currently observing. This brings us to the core of the issue. The true question is not whether the current fireballs are dangerous in themselves, but what their increased frequency implies about the unseen population of objects we are traveling through. If the rate of 1 to 1 0-meter objects is indeed 2.5 times the historical average and still rising, and if this reflects a genuine increase in the near-Earth debris population rather than a temporary stream crossing, then the rate for 2 0-meter objects is also elevated. By extension, the rate for 5 0-meter objects is also elevated. This does not make a Tunguska-scale event imminent tomorrow, but it is enough to shift the entire probability distribution in a direction that warrants our undivided attention. And at the moment, we are not fully paying attention. To be clear, the planetary defense community is making serious and tangible progress. NASA's DART mission successfully demonstrated our ability to deflect an asteroid with a kinetic impactor. New space-based survey telescopes are being developed to push our detection thresholds down to smaller and smaller objects. This progress is real and commendable. The challenge, however, is one of timelines. These vital detection systems require years to become fully operational. Yet the anomaly is unfolding in the here and now. The current situation also exposes a deeper, more systemic vulnerability in our approach. Our entire detection architecture was conceived and constructed based on models of the near-Earth debris environment as we understood it when those systems were designed. It was built for a certain definition of normal. If that baseline has fundamentally changed, if the background we are moving through is now denser or differently structured, then our instruments may no longer be optimized for the reality we face. This raises a critical question. Are our current survey systems, designed for a quieter past, capable of detecting the subtle but profound signs of a new and more active present? If the answer is no, the implications of this anomaly could extend far beyond the spring of 2026. When the very environment we are observing begins to change, our methods of observation risk becoming obsolete. If the background rate of celestial debris is shifting, if new streams of material are forming, or if our corner of the inner solar system is simply denser than our models have long assumed, then our detection systems designed for a different reality may be systematically missing the most important features of this new one. The data is unambiguous on one point. We are encountering more objects than usual. The fundamental question is why? The scientific model that was meant to explain this phenomenon concluded 3 weeks ago, yet the anomaly has persisted. This leaves us wondering what might come next. We find ourselves in this position not because the science was flawed, but because the science has not yet adapted to what the raw data is telling us. This is the precise nature of our current situation. Not panic, not certainty, but the specific kind of uncertainty that arises when you stand at the very edge of what your instruments and models were designed to comprehend, peering into a territory that is clearly present but remains entirely unmapped. The sky above Buenos Aires was illuminated on April 27th. Just 2 days later, the same happened over British Columbia. In that same period, the skies over Hawaii displayed their own unusual activity. Yet the model had predicted this window of activity would close 20 days earlier. Compounding this mystery is the knowledge that our databases undercount these events, meaning the true rate is almost certainly higher than official figures suggest. Our detection threshold also means that objects of the same size class are, right now, approaching Earth completely unseen. And the best scientific explanation we had, as robust as it was, fails to account for anything that has occurred since April 7th. From this vantage point, we can imagine two possible futures for this story. In one version, everything resolves itself cleanly. The existing model is extended, a second debris stream is identified, and our data eventually catches up to the events on the ground. In this scenario, the April anomaly is explained, archived, and filed away alongside other solved cosmic mysteries. The baseline rate of fireballs decays, and the spring of 2027 looks much like any other spring in the historical record. The solar system, it would turn out, was just passing through a temporary phase. This version of events might well be correct. But there is another possibility. In this alternative version, the pattern we observed in April is not a temporary deviation, but a new persistent signal. It would mean that what we are experiencing reflects a genuine, ongoing change in the debris density of the inner solar system, a change our survey systems were not built to detect. Our models were not designed to predict, and our current infrastructure is not equipped to provide warnings for. This version is also possible, and perhaps more so than we are comfortable admitting. What can be stated with confidence is where the science stands in the late spring of 2026. We are faced with a sustained 2-month spike in fireball activity that has now surpassed the timeline of the only peer-reviewed explanation available for it. We have a global geographic distribution of these events that is inconsistent with the theory of a single, isolated stream of debris. We have observations of the Anthelian source doubling, which predates the peak activity and suggests an elevated background rate that goes beyond any specific identified stream. All of this is viewed through a lens we know to be imperfect. Our detection architecture has known structural blind spots that systematically undercount the very events we are trying to analyze. Our databases have documented accuracy problems at the precise size class most relevant to the current anomaly. And, perhaps most unsettling, we have an asteroid that recently passed inside geosynchronous orbit without a single advanced warning being issued. What we do not have is an explanation that can tie all of these disparate threads together into a coherent, verified, and predictive account of what is happening. That comprehensive account does not exist yet. It is being built, piece by individual researchers working with incomplete data and insufficient funding to move any faster. And while it is being built, the sky continues to do what it has been doing since March 16th. There is something particularly striking about the Buenos Aires event. 13 million people saw their night sky light up with a brilliant green glow. They looked up, almost all of them instinctively, the way humans have always looked up at a sudden light in the darkness. They witnessed something real, something that moved faster than anything they had ever watched cross the sky, brighter than any weather phenomenon, and stranger than any human-made light show. For a brief, electric moment, they experienced direct contact with a universe that normally keeps itself at a polite, astronomical distance. And then, it was over. None of them knew that the model that should have explained it was already 3 weeks past its expiration date. None of them knew that the database that should have captured what they saw holds no record of their shared experience. And none of them knew that somewhere in the same solar system, other fragments from the same or similar debris populations were tracing their own invisible paths through interplanetary space. Whether those paths would intersect Earth's again tomorrow or in 1,000 years was a question to which the only honest answer is, we do not currently know. They just looked up, the sky turned green, and then it went dark. The universe, it must be said, is not required to behave according to our models. It never has been. The history of science is largely the history of reality outrunning our descriptions of it, a story of models that worked perfectly until they didn't, predictions that held true until they broke, and maps that reflected the limits of our understanding, rather than the territory itself. The M2026A1 model is simply the latest chapter in this long history. It was good science, representing the best available knowledge we had. But the sky over Buenos Aires on April 27th was entirely indifferent to any of that. There is something both humbling and profoundly clarifying in this realization. We have built extraordinary tools. We have mapped the solar system with a precision that would have been incomprehensible to any generation before us. We have sent spacecraft to every planet, landed instruments on asteroids, and imaged the surfaces of comets from close range. Our understanding of orbital mechanics is so detailed that we can predict planetary positions centuries in advance. By any historical standard, what we know about near-Earth space is truly remarkable. And still, a green bolide crossed the sky over 13 million people in the middle of a late April night, 3 weeks after the only model that could explain it said it should not exist. The database did not capture it. The detection systems did not see it coming. The model's window had closed, and yet the sky lit up anyway. We know we are encountering more objects than usual. We simply do not know why, and we do not know what comes next. This is not a comfortable place to be, but it is an honest one. And the first step toward building the kind of science that might actually provide us with better answers is to be honest about how much of the picture we are currently missing. Future planetary defense requires us to build new tools and theories by consciously addressing our blind spots, the dark data, detection flaws, and model boundaries. The Earth is currently traversing a region of space that our best predictive systems did not fully anticipate. This fact should not inspire alarm, but rather serve as a profound motivation to work with greater diligence. It is a crucial reminder to stop mistaking the edge of our knowledge for the edge of reality itself. For whatever we are passing through, it remains entirely indifferent to the limits of our understanding.